these two solutions. Okay, so we worked this problem out last time, just reminding you that if it can be factored, if a quadratic equation, or rather the polynomial side of it, can be factored, then you can easily, like relatively easily, find the zeros, right? Okay. Now, this applies to, now I'm going to erase this one. I know it's not been up here for more than a few seconds, but we already did this problem last class. Now, here's one. That can be factored by the grouping method. And I just wanted to, I can't remember if we did one of these last time or not, so I just wanted to remind you that you can also solve these, even the more tricky factoring ones, you can still solve by factoring. Just by, you get it down to those two factors and then you split them. So I'm going to say in between here, this would be a good one for you to try on your own. We've done enough factoring by grouping examples that you can go. In fact, we may have done this exact one, I can't remember. But you can go back to your notes, reference your notes later, and fill in the steps in between. But you should end up with this factored version. Now, I wanted to point something out. You can get from here to here without using the grouping method, just by kind of like brute force. You can brute force your way through it just by thinking about like what numbers would go into these parentheses and then just trying different numbers and stuff like that. And if you've got a good feel about how to multiply this out and how it multiplies out to yield something like this, then you can brute force your way through it without using any kind of fancy techniques like grouping method. I just want to point that out. That's legitimate. It doesn't work every time, and it usually takes more time, but you know, that's just an option. So here we would set each of these factors, linear things, equal to 0. The right-hand one is just a matter of subtracting 1 from both sides. So the root here, the solution, is x equals -1. Over here, you've got to subtract 3 on both sides first. So remember, we're isolating x here, going to subtract 3 from both sides. It effectively scoots the 3 across the equal sign and makes it negative. And then I'm going to divide by 2 on both sides to cancel out the product of 2 and x here. This is 2 multiplied by x. I want to do the inverse operation of that on both sides. In other words, divide by 2 on both sides. So those are my two solutions for this quadratic equation here. All right. 1 second. I'm going to just take roll. Oh, so slow. There we go. Download attendance. Okay. There we go. This is solving a quadratic equation by factoring by grouping. Now, the question we left off with last time is, can you always solve one of these by factoring? And of course the answer is no, right? Because if the answer was yes, then we wouldn't still be talking about them, right? In general, something like this with just generic ABC cannot be solved by factoring. It's only special problems that typically like your instructor or your textbook is going to make up for you that act nice so that you can then factor them. So here's an example of one that cannot be factored. Cannot be factored because, well, first of all, this looks like one of the easy ones, right? Because it's got a leading coefficient of 1, x squared plus 5x plus 1. But you need two numbers such that the product is 1 and the sum is 5. Well, there's no way to make that happen with nice integers. Like, you're not gonna, there are solutions to this, but they're crazy looking. They're not like, you know, like 2 and 3 or something like that. It's gonna be really wild square root numbers. They're gonna be irrational. Okay, so what do? Do we just say like, can't be solved? No, we have a formula for it. And I told you last time that we were going to derive it, but I've changed my mind again. I'm just gonna, because I really want to get through section 1.5 and have time to talk about some of it today and on Friday, and also leave a little bit of time, hopefully, for questions and review before the exam. So I want to just proceed straight to the quadratic formula, which is going to be the tool that works for any quadratic equation. So I'm going to erase this for now, but we'll come back to it. I'm limited by space, so I've got to erase it, but we will come back to that particular one. To solve this equation in general, we use the quadratic formula. And it's going to yield two solutions, because remember, in general, these can have two solutions. They can also have only one solution, or they can possibly have zero solutions, but we'll talk about a little bit more about that in a minute. In general, here's the first solution. It's going to be, let me back up a little bit. Let me come over here. The negative of that linear coefficient, so negative b, plus the square root of that same term again, squared, minus 4 times that linear, times the leading coefficient times the constant, c. So under the radical is b squared minus 4ac. This part's actually going to be important later. We're going to talk a little bit more about this particular piece of it later. And it's all over twice the leading coefficient, so 2a. Okay, so a nice compact little formula there for one root. And the other root, the other solution is going to be, if you've seen this before, you know what it's about to be. It's going to be the same thing, negative b, but it's minus the square root of b squared minus 4ac. All right. Give you a second to write it down, and then we're going to practice using it. Like the rest of this section is going to be all about the quadratic formula. Now, you might look at this and say, well, it looks kind of bad at first, but we're going to practice it, and you'll see, you know, it's just a matter of making sure your algebra, your arithmetic really is on point. And you might say, well, why wouldn't you just always use the quadratic formula? And the answer is you can, like even with something that can be easily factored. So okay, so consider, let's say example 1. Solve x squared plus 7x plus 12 equal to 0. Now, typically, I would say solve this by factoring, because that's going to be probably the most efficient way, the most natural way to solve this. In fact, we already know the answer, right? But let's just for practice, solve that using the quadratic formula, which I'm going to say QF, quadratic formula. What do you need to do first? You should identify what are the pieces inside of the quadratic formula. There's A's, B's, and C's. So we need to figure out corresponding what the A, B, and C are for my given equation here. So A is going to be the leading coefficient, which is 1. B is going to be 7, the linear coefficient there. I say linear coefficient because it's attached to the, oh, I hope you guys can see. Let's see. Yes, barely. Do I need to tilt up? I can't really see what you guys can see.
It's fine for me.
Okay, Cool, thank you. And then C is 12. Okay, so now it's just a matter of plugging in, and often you will see the quadratic equation, the quadratic formula, this thing, written compactly just by saying, you could say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, and then you don't have to, what this does is it just writes both of them just together. So you may see it written this way too, by the way. But what I want to do now is solve this thing by plugging in my solution. So first, I'll do the positive one. I'm going to do it in two pieces. I'm going to do the one that has the plus in the formula. So I'm going to say, okay, my formula is negative b, so I'm going to say negative 7, and then plus, now b squared, and I should wrap it in parentheses. That's my b squared, b is 7, minus 4 times a, which is 1, times c, which is 12. Oh no. Oh yeah, that's fine. Sorry, I just had a brain fart. Okay, 2a, which a is 1. Okay, there we go. I'm going to continue working horizontally here. So I'm going to have negative 7 plus, and then what ends up happening in the square root? 7 squared is 49. 4 times 1 times 12 is 48. So I have the square root of 49 minus 48 all over 2, right? It's going to be all over 2. Now you may want to write that as a separate step. Here you might want to write 49 minus 48. I'm just going to go ahead and say what that difference is, which 49 minus 48 is 1, right? I'm doing that because I'm very limited on space here. You may want to write an additional step and have this as your, as your next step. You may want to write that step in between where you say 49 minus 48. Okay, now I'm going to say that that's just, square root of 1 is just 1, right? Square root of 1 is just 1. So I've got negative 7 plus 1 all over 2. Okay, negative 7 plus 1 is negative 6 all over 2. So I get negative 3. And that checks out with one of the solutions we got last time. Right, you remember the solutions to this thing were negative 3 and negative 4. Okay, so I'm going to give you a second to write those last few steps down, and then I've got to erase. Okay. Now, my next setup is actually going to be exactly the same, right? Except it's just going to be a minus sign there. So now when you're in your next step in your notes, you're going to write x equals, we're on solution number 2 now, right? The second solution. And you're going to write this entire thing again, just like you just did, except with a minus in front of the radical, in front of the square root. And what's that going to come down to? It's going to come down to negative 7, and then minus the square root of 1. Because last time, nothing inside changed, right? This thing yielded square root of 1 when everything was said and done in here. And in between our two solutions, nothing is changing. So it's still a minus, or it's still a square root of 1 there. And the bottom is still at 2. Okay, and that's going to be the same as negative 7 minus 1 all over 2. Because again, the square root of 1 is just 1. So that's all that happened from there to there. And then if I have a negative and I'm subtracting from it, then I'm going further into the negatives. So I'm getting negative 8 over 2, which is negative 4. So I'm getting two solutions, x equals negative 3 and x equals negative 4. You probably agree with me that factoring this one is more efficient, right? Like, just factoring this is much more efficient. Going by quadratic formula, not the most efficient. Now, what if you can't factor the polynomial or the quadratic and use factoring to solve the equation? Well, then you have to use the quadratic formula. So let's do one like that. So here comes that equation I wrote down earlier, x squared plus 5x plus 1. This is example 2. Example 2. Solve x squared plus 5x plus 1 equals 0 using the quadratic formula. All right, how about writing down a, b, and c? A, again, is 1, just like it was last time. If the leading coefficient is not explicitly stated here, it's understood to be a 1. The middle coefficient, that thing attached to the linear term, is 5, and the c is 1. Now, I want to point out something. Whenever you're setting up your a, b, and c, make sure that you have a 0 on the right side. If there's anything but 0 over here, like if there's like a 2 or whatever, make sure you scoot it over and combine it with your constant term to make to have a 0 there. Because the quadratic formula is, it only accepts, it's only going to yield the correct answer when you give it the correct a, b, and c. And the quadratic formula expects for you to have your equation set up equal to 0. And it doesn't know if it's not equal to 0. It's dumb, right? It's just a formula. It's just a dumb formula. So you've got to know, you've got to give it the right inputs for it to give you the right outputs. So always make sure it's set up equal to 0. Sometimes you can come across a problem where it's not explicitly equal to 0, but it's just a matter of scooting things back across the equal sign to get everything on this side. Okay. So here we are. I'm going to solve this in a slightly different way this time, just to show you how it can be, how both solutions can be compacted into one. So this time I'm going to say negative b, so b is 5, so negative 5. Now I'm going to put both solutions together here by stuffing that plus or minus sign together, plus or minus, and then square root. B squared is 5 squared, then minus 4 times 1 times 1. 4ac, where a is 1 and c is 1. All over 2 times a, where a is 1. Excuse me. Okay. Next step is negative 5 plus or minus. You know, I can write all of this down without dealing with the root yet. I can say, I know I've got the negative 5, I copy over the plus or minus, I'm going to copy over the 2 in the denominator, because 2 times 1 is just 2. I'm going to draw my fraction bar, and I know there's going to be a radical. I can get this far without even computing anything for real, right? Just copying stuff over. Okay, but now I'm actually going to compute this. And again, I'm going to kind of skip the intermediate step here and just go ahead and find this difference. So I know that 5 squared is 25. Minus 4 is going to yield a 21. So you may want to write the step in between where it's square root of 25 minus 4. And then in your next step, you'll say this. Okay, now, what do I do at this point? Last time, how did I get past this point? I said, oh, square root of 1 is just 1, right? I had a perfect square number under the radical. But 21 is not a perfect square number, right? It's not. It's just not, right? It's kind of close to 1, but and it can't even be simplified either, right? There are no perfect square factors of 21. In fact, its only factors besides itself and 1 are 3 and 7. Those are not perfect square numbers. So this cannot be cleaned up at all. That radical cannot be cleaned up at all. So what do? Well, these are the solutions then. If you can't go any further, then these describe the solutions to this equation. If you really wanted to, you could split them like negative 5 plus square root of 21 all over 2. and x equals -5 minus square root of 21 all over 2. It's really the same thing though, right? It's just this is more compact, just a different way of writing it. But these are the solutions. So they're very weird looking, and that makes sense to us because we know that if we could have factored this, then it would have had nice clean answers, like maybe even fractional answers, which are okay. I'm still considering fractional answers like the last one we had a solution of -3 over 2. I'm still calling that like a nice clean solution, right? It's rational. But these are very irrational solutions. They've got a square root of a number that cannot be simplified, but they're still legitimate solutions. This means if we graphed, well, no, let's not get there yet. Okay. So that's it there. I'm going to give you one to try again. Where are we at on time? Yeah, we're doing fine. Okay. So let's do... Example 3, solve 3x squared. Let me think on the side. Minus 5x plus 4 equals 0. Example 3, solve 3x squared minus 5x plus 4 equals 0 using the quadratic formula. Okay, so A is 3. I need to change this. Hang on, before I get too much further. I don't want to do non-real solutions. 25 minus 4 times 3, yeah. 4 times 2 times 3. Let's change the 4 at the back to a 1. That we'll do it, yeah. Okay. Okay. A is equal to 3, B is equal to -5, and C is equal to a +1. Okay, so now we're going to set up the formula. X is -b plus or minus square root of b squared minus 4ac all over 2a. So I'm going to start off with -b. So well, I can start off with a big fraction bar. -b is going to be negative of -5. So of course, we'll clean that up in the next step. It's a negative of a negative, right? But try not to get too ahead of yourself here. Let's just plug everything in. Let's not skip steps as we're writing it down. Now b squared is just going to look like this, and then minus 4 times a times c, and then all over 2 times a. Okay. Cleaning this up a bit, negative means positive. 5 plus or minus, again, I'm using that compact notation, writing both answers at once, using the plus or minus thing. 5 plus or minus. Now, let me write the rest of what's going on here. There we go. Got the 2 times 3 in the bottom, yielding to 6. What's happening under the root? Well, -5 squared is positive 25. You square a negative number, it's -5 times -5, so it yields a positive. So that's going to be 25 minus 12. That's what's happening inside there, 25 minus 12. So I'm getting 13. And that's it. I mean, I could write each one individually, 5 plus square root of 13 over 6, 5 minus square root of 13 over 6. But if I asked you for the solutions to this quadratic equation, and this is what you said, x equals 5 plus or minus square root of 13 all over 6, that would be it. Yeah, that's it. So the quadratic formula is really nice. Now, I want to do one where we have to do more to clean up what is happening here. Like, we need to clean up the radical. So let me come up with one now. While you guys are thinking about this, I'm going to come up with one. Squared. Yes, I think that's what I want to do. Ouch. Okay. Next problem. Let's try 2x squared minus 16x minus, or actually, let's say equals 8. Example 4. Solve 2x squared minus 16x equals 8 using the quadratic formula. Before you write down a, b, and c, you need to note that it needs to be adjusted to 2x squared minus 16x. You need to get a 0. You need to isolate everything over here and get that 0 by itself. But the problem is there's an 8 there. But that's okay. I'm just going to subtract 8 from both sides. And since it's constant, it doesn't subtract from either of these terms, right? Since it's not a like term. So it just gets stuffed. Minus 8 next to the 16x equals 0. That's just one of those things that might happen where you have to adjust the equation before you identify a, b, and c. So a here is 2, b is negative 16, and c is negative 8. Okay, so these are the biggest numbers we've had to deal with yet, and there's more negatives. So let's do it together and see what happens here. X is equal to negative b. Okay. Let me draw my big fraction bar. Okay. Plus or minus square root of b squared. Then minus 4. So the 4 is part of the formula. The 4 is always going to be there initially. And then 4ac, right? So a is 2 and c is negative 8. Ooh, excuse me. All right, all over 2 times a, where a is 2. Okay, I am going to write that intermediate step this time. So I'm going to say 16 plus or minus square root of negative 16 squared. I know it's going to be positive, right? Because negative squared is positive. 16 times 16 yields 256. Now here, I see that I have a minus, but then a negative out here. So I know that the operation in between is going to be a plus. So I know that the operation in between is going to be plus because there's a minus sign here and a negation over here. So now all I need to worry about is what is 4 times 2 times 8? Well, that should give me a 64. All over 4. 2 times 2 in the bottom, yielding 4. So make sure you see where this is separating. This is the second step here. Right. Okay. I'm going to have to erase this. And now I'm continuing up here, but in your notes, you're just going to keep going down. I'm just very limited on space. So, all right, so I've got 16 plus or minus the square root. What's that sum? It's all over 4, right? That sum is going to give me 320. You can just bust it out on the calculator, right? 256 plus 64, 320. All right, now where am I? I'm back in 0.4 territory, section 0.4, having to reduce radicals. So I'm going to say square root of 320. I need a perfect square factor of 320. There's got to be one, right? I mean, look at that. That number looks super even. It looks like it's got some good factors in it. You can just look at it and tell. So, let's see. Do we think 16 will go into it? It'd be nice if we could get 16. That's a pretty big factor. So how do you know? Just take 320 and whip out the calculator, plug 320 in and start dividing it by perfect squares. I'm going to try 16. You know what? Actually, before I try, I'm going to try 64. Ooh, 64 works. Okay, good. So I've got 64 times 5. Nice. Okay. That's the same as the square root of 64 times the square root of 5, right? Splitting it around that operation. And that, of course, is 8. That's why I picked the 64, right? Because it's square root of 64 is 8. And then square root of 5 left over. Okay. So now my next step, I'm just going to keep erasing a step at a time as I go here, is going to be 16 plus or minus 8 square root of 5 all over 4. So the square root of 320 turned into 8 square roots of 5. Okay. Now I need to look for simplifying this fraction. Okay, I'm still not done. I told you we were going to do one, right, where there's lots of extra work to do past just the operations inside the square root. This is kind of where it gets the most involved, where not only do you have to take your square root on the side and clean it up, but then once you put it back in, you've got to look at the fraction as a whole and say, there's more I can do here, because I actually know that 16 and 8 have a factor of 4. Meaning I can pull a 4 off of both of these two terms. I can pull a 4 off of 16, and I can pull a 4 off of 8. If I pull a 4 off of 16, so hang on, let me write the rest of my fraction here. There's the 4 in the denominator, it's just along for the ride. If I pull a 4 off of 16, I got a 4 here, then my little plus or minus symbol. Now if I pull a 4 off of this term, I know there's a square root of 5 here, but it's okay, I can still pull stuff off via multiplication, right? I'm pulling it off as a factor, and that's going to leave me with a 2 square root of 5. Okay. Now, you see what I'm getting at, why was I trying to pull a 4 off? Because these cancel, right? So now I'm going to work horizontally here. These two 4s cancel, and you end up with 4 plus or minus 2 square root of 5. This would be, finally, the final cleaned up answer. Be careful of getting excited when you see common factors here and here. You have to be able to get the common factor out of both of the numbers up here, which we were able to do in this problem, but you won't always be able to do. Like, consider if it just worked out to be 16 plus or minus 3 square root of 5. You can't get a 4 out of the 3, so thus you would not be able to do all of this. You would not be able to clean it up as nicely. You've got to be able to, if you want to cancel this 4 or another factor of the 4, like a 2, you've got to be able to get it out of both of the top numbers, just like I did here. This is the appropriate way of doing that. All right. Let's talk about the discriminant. Changing gears now. Let's talk about the discriminant of the quadratic formula. What is the discriminant? Well, it's the b squared minus 4ac thing. The part under the radical. Okay, if it is, now we didn't do one like this, but if it is 0, what does that mean? Then we have a repeated solution for x. So we've worked out problems where we had repeated factors, and I think we even did work out a corresponding equation that had repeated solutions. So what I want you to do is for your own, this will have to be outside of class because I really want to get to the next section today. So to see this, find the solutions of, just go with this one, x squared plus 14x plus 49 equals 0 using the quadratic formula. To see an example of this in action where you'll see if you plug everything in right into the quadratic formula, you'll see that whole square root thing go away and you end up with just a single solution. Because how do you end up with two solutions? It's the plus or minus thing that's stuck in front of the square root. If the square root goes away, you just end up with one repeated solution, which, by the way, you should get -7. So, but work that out and you'll see what I'm describing there. Okay, I'm still talking about the discriminant. So here's the second statement. If it is greater than 0, like every single problem that we worked out today, the discriminant was not 0, right? It was bigger than 0. Then we have two solutions. This doesn't say if they're nice or not, right? I could say, if the discriminant simplifies into a perfect square, then that means we have nice solutions, but that's not really the point of this discussion. This is just discussing how the discriminant tells you how many solutions you have. If it's 0, you only have one solution. If it's greater than 0, then you're going to have two solutions. Every single problem that we worked out today has two solutions. That's why they all had the plus or minus thing. That describes two separate solutions. So I'm not going to give you an example to try here, right? Because we did like 4 of them already. Now, what if it is less than 0? Then we have no real solutions, but we can have, we will have complex solutions. So what am I talking about here? Well, if the discriminant is less than 0, then that means the thing under the square root is negative, right? If the discriminant is less than 0, what is the setting here? What am I talking about? What's the context here? That means the thing under the radical is negative, but we don't allow for that, right? Not in the real numbers. If we say square root of -2, then it's like that's meaningless in the real numbers, excuse me. But we can move into a greater number system, or well, a larger number system called the complex numbers that can describe complex solutions. And that's kind of so we'll say more about this coming back to the quadratic formula, finding complex solutions. So first, before we start talking about complex solutions to these, degree 2 equations, first, let's talk about complex numbers, because you may not have been introduced to those yet. So what I'm telling you is for our purpose, this class, the motivation is for talking about complex numbers is that they can be solutions to quadratic equations. There's way more you can say about complex numbers. In fact, they're even applicable in like stuff you may learn about if you take like an engineering or physics class. You don't have to go very far to find applications of complex numbers outside of math. All right, so this is section 1.5 now, complex numbers. Let's just talk about what they look like. A complex number is of the form. So what does it look like? Well, it looks like this: a plus bi. Okay, that's a plus bi, where a and b are real numbers. So it's built from combinations of real numbers, but with this special number I attached to it, which is now what I have to describe to you, right? Let me make that work. There we go. So what is I? So what is the I then? Well, the problem that I described a second ago with saying that there are no real solutions when the discriminant is less than 0 is that in the real numbers, we are not allowed to have negatives under square roots, right? So the complex numbers have to address that, right? That's the biggest issue that we're looking at here, is that you cannot have negatives under square roots. How do the complex numbers address that issue? I addresses it. I mean, the letter I. So I is equal to the square root of -1. It's basically saying, look, we're just going to say the negative under a square root, just let that be the letter I, and now you can talk about all these different numbers that can have negatives under the square root. I is equal to the square root of -1. Another way you might see it, if you look up what is I, someone might say I squared is -1. Which is another thing that doesn't make sense in the real numbers, right? Because we say if you square any number, it should be positive. But this is like saying, well, what if we identify this new number such that when you do square it, you do get a negative. So this opens up tons of possibilities for us. Before we get there, though, let's just talk more about the form here. In the form, A is called the real part. B is called the imaginary part. The part attached to I is called the imaginary part. Not including I, just the number attached to I. And I, by the way, did I say what its name is? It's called the imaginary number or imaginary unit. It's okay. So here's an example, just practicing using the form, just making sure we're comfortable with this. Example 1. identify the real and complex part. Do we say real and complex or real and imaginary? I'm going to say imaginary. Real and imaginary part of each. Okay, so example 1, part A, that's just identifying part A of example 1. Let's say 7 plus 2i. Okay, so the real part, which I'll denote with a, well, no, I'll say it, I'll write it out. Real part is 7, okay? It's the real part of it. And the imaginary part, which I'll just say im, just to save time, imaginary part is 2. Not 2i, just 2. Just 2. Okay. What if I just wrote negative 3i? Negative 3i. The real part, any guesses what the real part would be? The real part, since it is not written, would be 0, and the imaginary part would be negative 3. Okay. And I could do a similar thing and just say the number 5. And the real part is 5. And I'm getting to where you won't be able to see it. The real part here would be 5. And the imaginary part would be 0. Okay, so that's just the form of a complex number. That's the form of the complex number. Okay, we have time to do the next little part too, and that'll leave all of Friday to finish talking about complex numbers. And really to talk about how they can be solutions to quadratic equations. Example 2, use the imaginary number I, use I to simplify each radical expression. Square root of negative 16. All right, if I asked you this anywhere outside the setting of the complex numbers, you would say not possible. That doesn't even make sense. You can't have a square root of a negative number because there is no number that when you square it yields a negative. But I say, well, let's make the setting the complex numbers and let I be the square root of negative 1. Now you can work with it. So what do? The first thing you do is deal with the negative sign by pulling the negative off, and storing the negative attached to just an arbitrary 1 that I'm introducing, right? Negative 1 times 16 there. Now split the radical. And now remember that negative 1 under a square root the definition of it is I. Okay, there we go. So you just stuff the I out to the left of the radical, and then you deal with the square root part. Now in this case, the square root of 16 is 4. So we would say I times 4. So these are connected by multiplication. That's I times 4. But when you get a nice clean whole number out of it like this, we like to write it like as if it's a variable, kind of like an x, and we'll say 4i. If you have to leave it if it's an ugly square root that you can't deal with, so you have to leave a square root part, you leave it on the right. If it's a whole number part that cleans up and the whole number comes out, then you write it on the left. That's just tradition. It's, you know, it's just the notation. Okay, let's try square root of negative 320. Well, we simplified this earlier, right? So I'm gonna just pull off the negative. Not even gonna think about the square root of 320 yet. Whoops, 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 whoops. The negative is inside. Okay. Continuing, you can keep working down. I'm going to scoot up so that you can see it. Square root of negative 1 is I, and then I have the square root of 320 attached. But I actually worked square root of 320 out earlier. Square root of 320 is 8 square root of 5. So how do I clean this up? Just obeying the tradition, the traditional notation, I would say 8i square root of 5, putting the whole number on the left and the square root part on the right. This is going to be super important. This is going to be super important when we look at cleaning up the quadratic formula when it has when the discriminant is negative, because the discriminant being negative means that we're going to have negatives under the square root in the quadratic formula. So you're going to need to know how to deal with negatives under the square root so that you can clean up your solutions when I eventually ask you to find, on Friday, I'm going to ask you to find complex solutions to quadratic equations. One last thing here. One last thing about I, and then we'll go. The powers of I are cyclic, meaning that they repeat. When I say powers, I mean like exponents, right? They have a pattern. That's another way to say this. You start with I to the first power, we'll just call I, which is kind of meaningless, right? But it's going to fit my pattern better. I squared is -1. Now, what would I cubed be? I cubed is just the same as I squared times I, right? If you pull it apart, I cubed is just I squared times I, so negative I, right? So that's negative I. And then I to the fourth is the same as I squared times I squared, just using exponent rules. So I to the fourth is -1 times -1, which is 1. Then I to the fifth, it starts over. I've got I to the fourth times I, putting those together builds I to the fifth. So I've got 1 times I, it's just I. And it starts to repeat, or you start to see the repetition happening. So every fourth power of I, you get to 1. So I to the 12 would be 1. I to the 16 would be 1. And you can use this pattern to simplify really high powers of I, which I usually do. I don't think I'm going to emphasize as much this time because honestly, it's not useful. It's just kind of a cool little thing. I could ask you a problem like, what's I to the 511? And there's a way you could just decode the pattern to get there. But that's I'm treating that as an extra thing here. I still wanted to point out that it does repeat. There is a pattern, so that if you ever see the pattern, you won't be, if you see it outside of this class, you won't be completely flabbergasted when you see that. All right, that's all I got for you guys today. Stick around if you have questions. If not, I'll see you on Friday. And when I say see you, I mean in the, virtual lecture.